Hey, this is Ana Doblas for 513 Intro to Optics and Photonics course. In this video, we will describe rays by their height and angle, and we will use matrices to see how they propagate through arbitrary optical systems, including a 4F system. The main idea in matrix optics is that rays are defined with the height and a parameter. So this is gonna be the height of my ray and theta is gonna be my angle. So we can always define rays as a pair of values that is gonna be my height and theta. So the whole idea is that you have an input ray, right, with its corresponding height and angle passing through an optical system, and you're gonna have the output rays. So when we think this, we're gonna have my input ray is gonna pass through a system. Let me try to use a different color. So it's gonna pass through a system, an optical system that is gonna be defined by 2 by 2 matrix. We use the capital M value, so the M is gonna define the ray transfer function of the system. And it's gonna give us some output value with the height and its angle. It's gonna change based on the transfer matrix. So the ray transfer matrix is a 2 by 2, so we call it usually the ABC matrix. So this is gonna be our ABCD matrix. So every time that you hear about ABC matrix, means that your optical system is defined by a 2 by 2 matrix. And the idea is that your height is gonna both your height and your angle in the output ray depends of the initial or the incident angle and height based on the elements of the matrix. So there are some particular cases that they are really relevant. So remember, and I'm gonna try to do the same color, but our output is gonna be equal to my matrix A, B, C, D, and then my input value. So the particular cases is when elements of the matrix are equal to 0. So let's say that A is equal to 0. So that means that the output height of the ray is independent on the height of the input ray. So all the values, it's only gonna depend on the angle, and this is the property for focusing systems. The other case is when B is equal to 0. So that means that the height in the output ray does not change with the incident angle, and this is happening with imaging systems. C equal to 0 gives us that parallel rays remain parallel. So that means that the angles between the input and output are proportional, and that is the case when we're gonna have parallel rays in the input and output spaces. D equal to 0 forces that the output of the ray is proportional to the height of the incident. So that means when rays that they come from a singular point became parallel. So that's the case where rays, and we have here the optical system, and after that we have a parallel system. So for knowing more about how to solve the ray transfer metric in an arbitrary, we need to define particular matrices for elemental properties. So the first one is propagation. It can be in air or it can be in a medium that the refractive index is constant. But the whole idea is that so remember that my transfer matrix is gonna be A, B, C, D. So A and D are equal to 1, B is equal to D, and C is equal to 0. So that means that the rate does not change, the angle between the input and the output, it's exactly the same, there is only a change in the height. The other case is when we have refraction, right? So if we remember from the other videos, the Snell law, we know that when a ray travels through change the medium, then the refractive is gonna bend towards or away the normal of the interface, and the Snell reflection is gonna be reflected by D equal to the ratio of the refractive indexes and C and D equal to 0. We can have refraction of a spherical boundary. We talk about refraction in a spherical boundary in class number 4, where we need to know not only the refractive index but also the curvature of the spherical boundary, and we need to take care of the sign of the radius. The other case is when we have reflection of a planar mirror. So in that case we have the identity. It doesn't, for us, because the angles are exactly the same, we can assume that nothing has happened, even though we know that there is an inversion. The reflection for a spherical mirror, we still need to obey the angles are gonna be, the height is not gonna change, but the angle is gonna change based on the curvature, because it's gonna be related with it. And then if we have refraction, so if the light travels through a lens, we're gonna have a bending, so height stays the same, but the output of the angle is gonna change with the focal length of the spherical boundary. So now that we have defined our element or matrices for elemental elements, it's really important to know how this is gonna propagate, right? So in a system, we don't gonna have only one single element, we're gonna have a combination of them. So our output information or our input can be seen is gonna move through a cascade of optical elements. So at the end, we can define our total transfer function as a multiplication of the transfer function for the individual elements. So our output, and the way that you're gonna do the multiplication, you're gonna do backwards, so we need to see from the right to the left. So it's gonna be from the first element here is the element closer to the output, and then it's gonna be the elements closer to the input, and then multiply by our input element. So remember, this is gonna be our last element of the system. And this is gonna be our first element. So the way that you're gonna do the multiplication of the matrix, it's not from left to right, it's gonna be from right to left, from the output plane to the input plane. So thinking about this, let's do the first problem. So let's assume that we have a system. So this is our input, right? And go through a system. And the system is plotted there on the right side, and we don't want to know the output. They don't tell us anything about the input rate, but we want to estimate the rate transfer. So my system, if we see from the input plane, this is my input plane, and after the length, this is my output. So if I have my matrix, what I have is, and remember, we need to go from right to left. So the closer element that we have from the output is a length, right? So we have a length of focal length f, and then we have a propagation of a distance p, right? So 1 from the lens is 1, 0, minus 1 over f, just because it's a converging lens, 1. And the propagation is 1d, 0, 1. And if you do the multiplication, you're gonna have 1d minus 1 over f, 1 minus d over f. So A equal 1, B equal D, C equal minus 1 over f, and D is, I'm gonna write in a different way, so I'm gonna say f minus D. So let's talk about a little more about the microscopic system. So the microscopic system, it's a microscope is composed with a infinity corrected microscope objective lens. So we put the object at the working distance. And then light emitting from the object gets collected with the microscope objective lens, and because it is infinity corrected, we're gonna see a clear image of the object at infinity. But because we don't have access to the infinity, we need to use a tube lens, the TL, to bring that image at infinity in the back focal plane of the tube lens, right? So the image plane is the back focal plane, or the image focal plane of the tube lens. And in the image plane is when we find the clear image of the sample, so it's completely in focus. So this is, in general, the microscope objective lens is composed by a lot of lenses for correcting aberrations, but in a general case, we can assume that it's composed with a single lens with no aberrations. And the configuration with the system is every plane is separated by the focal length of the particular lenses. So it's called, this technique is usually called 4F system. So when we use it, the 4F system, is because instead of having a different focal length between the microscope objective lens and the tube lens, we have all the two lenses have the same focal length. So there is a propagation distance between the image and the object plane that is equal to the 4S system. So 4S systems are microscopes systems, just that we are assuming that now the focal length between the two lenses is different. So let's see more about what is going to be the ray transfer system, the ray transfer matrix of the system. And for this, the first thing that we're going to do, we're going to ignore the aperture stop. So this stop is going to filter some frequencies of the object, but we're going to take care of this, of the shape of the stop and the input, in module 4, which is about Fourier optics. So just, you can go to module 4 if you want to know more about it. But again, we're just gonna go from the transfer matrix, we go from the image plane to the object plane. So we're gonna build our system M, and what we have is, we have a propagation from the image planes to the tube lens. We have a propagation of FTL. Then we're gonna meet a lens that is gonna be with a focal length FTL, and then we're gonna have another propagation of FTL. So that propagation is gonna be from the tube lens to the aperture stop. After the aperture stop, we're gonna propagate a distance f m sub o propagation. That is gonna be from the aperture stop to the microscope objective lens. Then we're gonna meet the microscope objective lens, and we're gonna have another propagation from the objective lens to the object plane. I cannot do this, but I did this because to have more similarity, symmetry with the matrix, but these propagations you can do from the tube lens to the aperture stop, and then the aperture stop to the objective lens, or you can just consider a single propagation that is gonna be the distance, the sum of both focal length. Like, both approaches are completely fine. So if we do this and we put, then we're gonna have here 1 FTL 01, and then we're gonna have, we are considering converging lenses 1, then we have exactly again the propagation, and then we have the propagation of the focal length of the objective lens. The objective lens, and then we finalize, do the propagation to arrive to the object plane. And we can solve all these metrics. So the reason that I say to do it like this is because we can have the 2 right here. So this is gonna be 0 FTL minus 1 over FTL 0, and because we have completely the same replica, we're gonna have 0 FM0 minus 1 over FM0 0. So our matrix is gonna be FTL over FM0 0 0 and minus FM0 over FTL. But we can think this as a lateral magnification 0 0, and then the angular magnification. So ML is minus the focal length of the tube lens over the focal length of the objective lens. So this is the lateral magnification, how much the high change from the input to the output. And then the angular magnification is just the inverse of the lateral magnification, meaning that if the lateral magnification increases, then the angular magnification decreases. So we're gonna have less discrimination. Things that I want you to kind of see is that C and B are equal to 0. So B equal to 0. So B equal to 0 is for imaging systems. That's okay, but C equal to 0, it's for parallel system remains parallel. So that means that if we are illuminating, let me try to use a color. So if we are illuminating with a plane wave, right, we know that it's gonna go through the objective lens. Maybe that ray is no. It's gonna go through the objective lens. Let me do the parallel right here. So it's gonna meet the objective lens, and it's not, because it's going to the focal length, it's not gonna convert, and then we're gonna have, because it's that point is also the focal point, the back focal point of the microscope objective lens coincides with the front focal point of the tube lens, then at the end we're gonna have also a parallel beam. So that is the reason why C is equal to 0. Parallel beams remains parallel in both in the input and the output systems, and that's where usually we call the telecentric systems. Nonetheless, in general systems that they are imaging systems, what we're gonna define is we're gonna define a transfer function that is gonna be A is gonna be the lateral magnification. It's an imaging system, so B needs to be equal to 0. C is gonna be P, which P is the optical power. And in general, for this system, P is different than 0 if the distance if the distance between the tube lens and the microscope objective lens is different than the focal length, the sum of their focal length. And then the angular magnification, and remember that the angular magnification is just the inverse of the lateral magnification. Alright, this is how you know now about ray optics and matrix optics, and how we can know the features of the ray after going through a cascade system of optical elements.